So good morning, everyone. Welcome to the webinar. To our friends in Europe, good afternoon, and to our friends in Asia, good evening. My name is Madan Jagannath. I am the moderator today. The subject of the discussion today is the key high-density design considerations for high-reliability 5G radio access networks. What we will be talking about today is the challenges posed by the 5G network evolution to printed circuit board boards and the assembly of such. Basically focused on the radio access network for the deployment support challenges that OEMs and operators face, and then product design considerations. Before we get started, a couple of housekeeping things. The audience will be muted for the duration. If you want to ask questions, please use the Q&A function of WebEx to ask the questions. And those questions will be addressed after the main presentation is over. Our speaker today is Charlie Martin. Charlie is with Dell Technologies as a product manager for the Open Radio Access Network products. Charlie has been in the wireless industry for a good long time. Before Dell, he was at Award Solutions for a number of years, where he was the prime for their 4G and 5G RAN solutions, including all aspects of what constitutes 4G and 5G networks. And prior to that, he had leading roles in product management at Ericsson, Sprint, Huawei, and Nortel. So this has been, what we have today with us as a guest speaker is a real wireless industry expert. Now, before I turn this over to Charlie for members of the audience who are not members of HDP, I'd like to say a few words about HDP. High Density Packaging Group has been around since 1993. The group is focused, an industry consortium that's focused on printed circuit board technology. So the materials and methods of creating the high density products that we all enjoy and use every day. The approach is a collaborative approach where members participate actively in projects to evaluate technologies that are of interest to the members. So that's a key thing is the active participation. It's global membership. We look at environmentally sustainable products and things like that. There is great benefit that comes out of getting an unbiased assessment of any new technology. And that's one of the key aspects of what we do, is that since we have members who are across the ecosystem, from OEMs to material suppliers, we can get a very good evaluation of new technologies. So a few words on HDP, and now I will turn it over to Charlie for the main event. So Charlie, please take it away.
Thank you, Madden. What I'd like to do to start off is just talk about what our vision is for the architecture for Open RAN. So what's happened in the industry over the last 20 years is what I call at least in the RAN, the radio access network, is the disaggregation of it, or the breaking apart of the radio base station into its component parts. And what we saw happening about 15 years ago, we first started to disaggregate the base station from a monolithic box that had the radio function, if you will, and also the baseband function in two separate units called the radio head, or the radio unit, or the RU, and then the baseband unit. And saw a lot of success using that, taking the baseband unit down at the bottom of the tower, having the radio at the top of the tower, using fiber to interconnect them with the CPRI interface, and getting some real benefits and performance improvements by running fiber up the tower instead of coax. And then we saw, starting about 6 or 7 years ago, especially here in North America, is operators starting to do what's called densification with HetNet using CRAN and centralized RAN, where you take that baseband unit You take it away from the base of the tower and you pull it back to a centralized location. An older term was baseband hotel. More modern term is C-RAN hub site. And so you bring that back to a central location, a facility, and you get some real benefits from that. And that really started out in, I would call it dense urban and urban areas where it made sense to, one, operators had to get on top of the heavy capacity hotspot that's in the dense urban downtowns, dense urban and urban downtown areas. And instead of trying to continually try to cover that with macro cells, you break up that area into much smaller coverage areas using small cells. And then you go ahead and you run fiber out to those small cell locations. You bring it back to that centralized location, called a C-RAN hub site. And then you get some real benefits from doing that, from that architecture, some real performance and also cost benefits. So having said that, now where are we going? Now we're gonna take that baseband unit and we're gonna break it up. And so from the left-hand side, position one, I show the radio unit, and we called the base station the E node B in 4G, and now in 5G we call it the G node B. And that radio unit is going to be there in the tower. And what's interesting about it is there's going to be a lot of deployments of 5G that are very similar to 4G today, 20 megahertz or less carrier bandwidth, RF carrier bandwidth, 4x4 MIMO or less in terms of the MIMO scheme. A lot of that, but what's really coming out that's driving a lot of attention is this stuff here. I show 5G millimeter wave and sub 6 gigahertz millimeter wave, and some of the sub 6 gigahertz spectrum, particularly what we call C-band, is where we're going to be able to apply some advanced antenna techniques that we've not really been able to do at scale in the past, particular beamforming and massive MIMO. Okay. At position two, I show what's called the distributed unit. So the baseband unit is now split in the new disaggregated architecture into a distributed unit, or the DU, and the centralized unit, or the CU. DU being at position two, CU being at position three. The DU, in our view, it has to be it can't just be any type of server. It needs to be a hardened, reduced form factor server because of the many different environments it has to live in. Some of them are tough environments. It needs to be able to host multiple RAN technologies, 4G and 5G, theoretically 3G. Will also be as a potential here to do what we've been doing in core for a while, which is applying virtual network functions, right, to the RAN and cloud network functions. And depending on where the DU is based, makes complete sense to virtualize the software. Okay. Also, we've heard of something called MEC, or multi-access edge computing, which is basically a standardized by ETSI, right? A platform for the application server, right? And that MEC unit can live at multiple locations. I've seen it position 4 at the core location. I've seen it position 3 at the near edge, but it also can be at position 2 at the far edge. And also with some of the new things that are coming out, local breakout capabilities with enterprises, instead of having to have your data go up into the core network and out across the internet, it can be contained to the enterprise. So position 2 is the distributed unit, and also I show here that the MEC platform is integrated here at the far edge. But again, it could be at position 2 or 3 or 4, depends how the operator wants to do that, and also looking at the trade-offs on cost versus performance, all right, versus the application. At position 3, I showed the centralized unit, and I showed that at what we call the near edge. Okay, I've used those terms as near edge and far edge, and I'll get more into that in a little bit, especially for the far edge. But we see that the centralized unit, it's called the centralized unit because it's supposed to be centralized, all right, and Standards has done a really good job, I think, of looking hard at this disaggregation and where to place the pieces to get the best trade-offs of performance versus cost. So by placing the CU here at this more centralized location, we can definitely take advantage of some features that required centralized coordination, such as carrier aggregation, intercell interference coordination, or coordinated multipoint. Okay, And those features can bring much desired spectral efficiency and capacity improvements. And again, here, this is ideal, this CU is ideal to implement as virtualized network functions. And then position 4, we have the converged core, right? And that is our end-to-end view of what the next generation architecture is going to look like. So Madden, could I ask you to flip the chart? So my view here is that we have 4 main deployment scenarios. The 2 at the top are connected. The 2 at the bottom are connected. So up here, I'm looking at the dense urban grid with millimeter wave small cells. I showed the centralized unit as always being a centralized location. Now, what I'm doing here is I'm matching up terminology. So near edge and far edge is a very typical term. All right. And let me see if you mind clicking that one more time, Madden? There might be some. Oh, I'm sorry. Go back again. Okay. So here we show the regional cloud. That is an O-RAN alliance term, regional cloud. We map that to the near edge. Okay. And then we have what's called the edge cloud out here, and that maps to the far edge. So centralized unit always at the regional cloud or near edge, and then the DU always at the edge cloud or far edge. Okay. Now there's some differences here. So again, CU always centralized. DU could be at the far edge or the edge cloud. It can also be integrated with the radio head. All right. So these are the kind of the main things that I've seen in the marketplace is that first deployment scenario here, DU at the edge cloud in a temperature controlled environment. And then it ties into what I call an antenna integrated radio head or AIR device. And the reason that's done is that we're operating at very high frequencies, millimeter wave. Okay. And for millimeter wave, the losses are so high in terms of circuit board design, or if you're trying to use coax between 2 different enclosures, if you will, one having the radio head and one having the antenna, there's too much loss. There's too much loss. So what we do is we integrate them together into one device, a radio head that's actually got the antenna panel, right? And then potentially here also the DU. So these first 2 scenarios up here for dense urban grid, down here in sub-6 gigahertz. So for some cases, it'll be what I call the standard deployment, a separate radio head, separate antennas, coax in between, right? DU in a temperature controlled environment, but also the possibility to do the antenna integrated radio head deployment. And this is for particular parts of the sub-6 gigahertz. It's not for what they call low band or your typical mid band around 2 gigahertz, but around C band, around the 3.5 gigahertz to 4.7 gigahertz region, we can go ahead and deploy with antenna integrated radio head technology. So these are the 4 main deployment scenarios that we look at. Next chart, please. So digging this in a little bit more, and really concentrating on where the DU is going to go, we have 4 different scenarios here. Okay, the top left-hand side is what I call the outdoor cabinet. This is actually the toughest scenario. These are the 3 scenarios. The DU can reside in a environmentally controlled environment, as in like temperature controlled. So could be in a cell site shelter, could be in a building, or could be in a CRAN hub site. These are benign environments here. This other 4th scenario here, the outdoor cabinet might be a benign environment. It could have air conditioning and heating, but it also many times might just be basic fans blowing ambient air through the enclosure. And so if the temperature outside is hot, it's blowing hot air through the enclosure. If the temperature outside is cold, it's blowing, well, hopefully it's not blowing cold air through the enclosure, because it's really cold outside, you don't need much help. But so we're looking at our DU, where does it have to go and what are the requirements? And so a little bit more, we show here what I call the combo CU-DU deployment, which is kind of counterintuitive. This is not the disaggregated solution. This is a CU and a DU software together on one DU chassis, all right, one DU server. So what's the CU and the DU together? That's a BBU, right? So believe it or not, some early 5G deployments, some of the operators are looking at, I just want a 5G BBU to be slotted in place of 4G BBU. Okay, so that's the scenario here. Here on the cell site shelter is, let's be direct, right? Okay, so the outdoor cabinet is something that a cell site technician or field engineer cannot climb into. There's no environmental protection for the person working on it. So this could be, let's call this 20 square feet. Let's call the cell site shelter 200 square feet, 10 times the size, right? So call it 10 foot wide, 20 feet long, 8 feet tall. Environmentally protected, the cell site technician or the field engineer can go inside, close the door, and be protected from the elements. So we show it this as disaggregated. We show the CU being back at a data center or and there's different classifications, regional data centers, MITSOs, et cetera. Bottom line, we're just calling this a data center. Here with the indoor building cabinet, very similar, DU inside a building closet or a room, CU back at the data center. And then here, we have a CRAN hub site, okay? And then with the data center here. And so the difference here again, so if this cell shelter is 200 square feet, let's call a CRAN hub site a 2,000 square foot facility. Not as big as a data center. Let's call a data center a 20,000 square foot facility. Let's call this a 2,000 square foot. Okay, so it's a matter of understanding the size, how much space is available, and what are the environmental needs. Next chart, please. Ben. So what we do is we analyze four main morphologies. We analyze dense urban, suburban, and rural environments. And then we make our projections. So for dense urban, the server is going to be in a building cabinet or CRAN hub site. For urban, same thing. For suburban, could also be in a CRAN hub site of medium density. So CRAN hub sites are not all created the same. You can expect in dense urban downtown areas that they'd be of high density, as in many, many sites to be homed back to that CRAN hub site. Well, centralization also makes sense in other morphologies, not just dense urban or urban, but also suburban. So could be in what I call a medium density CRAN hub site. And then going out to rural, could be a low density CRAN hub site, but also here's where the outdoor cabinets come in. And this is not a hard and fast rule. You could have outdoor cabinets in suburban as well. There's never, this is really based on you have to work with the operator themselves and how they decided to deploy their facilities. Okay, so what we do is we look at these four morphologies, and then we say, what are the requirements for the CU, the DU, and the radio head? Next chart. So one of the things we have to look at, and this is really the start of your analysis, is what is the spectrum that's going to be used for 5G? And so we have our typical spectrum choices here in the US, and we have completely analogous matching spectrum choices in other parts of the world. Doesn't matter whether it's in Europe, Asia, Africa, wherever you go. We all have what? We all have low bands, right? So here in the US, you see 700 megahertz used a lot for LTE, 850 megahertz traditional cellular. You have 600 megahertz that came out a while ago. You have the same equivalents in Europe and Asia and other countries. So we have low bands. We also have mid bands. You see a lot of stuff here. So here in the US, AWS, Advanced Wireless Services, which is 1700, 2100. PCS, Personal Communication Services, 1900 megahertz. We have 25 megahertz TDD, a lot of that here in the US. And now we have all the C-band stuff coming out and also the CBRS stuff. Okay. So again, in Europe, analogous terminology, we have 1800, we have 2100, we have 2600, also C-band coming out here. And so all these things, this low and mid bands, that constitutes our FR1, our frequency range 1, that's defined by 3GPP, third generation partnership project. And so this is all sub 6 gigahertz, all sub 6 gigahertz. But this is where we have to peer a little closer and look at, well, where's all this fancy new stuff coming? Where's this millimeter wave and massive MIMO stuff coming? Well, the massive MIMO stuff is coming here in this CBRS to C-band range. Okay. And then we have our high bands, and that's our millimeter wave spectrum, 20 to 70 gigahertz, which is crazy talk. You know, I've been doing this for over 30 years now. To imagine that we can deploy at RF carrier, our RF carriers up in the millimeter wave band is kind of mind-boggling in a lot of ways if you're a radio geek like me. But we're doing it, right? And this is frequency range 2. Okay, and the reasons why we're doing this, we got to be really direct. Millimeter wave has enormous chunk of spectrum up there. So does C-band. Okay, next chart. So let's take a deeper look at advanced antenna techniques. So we've had some of these techniques forever. Receive diversity, transmit diversity. We've had those ideas since back in 2G, right? When I used to work in CDMA back at Nortel, we were doing receive diversity, and that improves the airlink reliability. And then you can also do something called transmit diversity, also increasing airlink reliability. We've been doing this all along in LTE, and that will still be done in 5G as well. And so you don't hear a whole lot about that's kind of in the background. It's been there for forever, these ideas of diversity techniques. So, but what's coming, what happened in LTE is that we were able to deploy MIMO, right? And lower order MIMO, single user MIMO, which means that your multiple MIMO streams, whether it be 2 streams or 4 streams here, they all get dedicated for single user. We use the term single user MIMO. What does that do? It improves the user speeds. 2x2 MIMO will give twice as user speeds as no MIMO. 4x4 MIMO on the downlink will give you another doubling. It'll be twice the speed versus 2x2 or 4 times the speed of no MIMO. And so we've been doing that for a while in LTE. We started out with 2x2, and then over the last 5 or 6 years, operators started deploying 4x4, and so that's been used all along. Bear with me for a second. I'm going to get a drink. But now, what are we hearing a lot about? We're hearing a lot about beamforming and massive MIMO. These ideas again are not new. When I was at Nortel back in 1999, my first job was being the product manager over our smart antenna portfolio that would do beamforming. Well, it never really took off for a long time because of a number of issues, cost, size. Those being the 2 main things. We never really had the right set of circumstances come along to provide the opportunity to really take off with beamforming. What really provided the opportunity here in 5G to begin with is these higher frequencies. When we went to millimeter wave, all right, we got such much higher bandwidths, and also because of millimeter wave spectrum, because the frequency range is so high, the wavelengths get very small. There's a relationship, inverse relationship between frequency and wavelength. The higher the frequency, the smaller the wavelength. The smaller the wavelength, the smaller the antennas get. It turns out that with millimeter wave, the size of the antenna elements can be tiny. Because it can be tiny, you can put many of them in a relatively small enclosure, and you needed to have all those antenna elements to do any kind of decent beamforming with accuracy. Okay, so this has taken off. We've seen in millimeter wave beamforming with lower order MIMO schemes has taken off. And what does beamforming give us? It gives us huge advantages in the network. Much improved channel signal to interference plus noise ratio. That is the #1 KPI when you're looking at airlink quality. It's channel SINR. Okay, what does better channel SINR give you? It gives you the opportunity to use higher MIMO schemes. It gives you the opportunity to use higher order modulation. It's basically improves everything. Better coverage, better capacity, better throughput. All right. Also, beamforming, instead of you've got these traditionally 3-sectored cells, or excuse me, 3-sectored E node Bs or G node Bs. Sector, also the term is the equivalent. Actually, the correct term is cell. Okay, 3GPP. The term cell means sector. Okay, So what we've always had in the past with the three cell model is antenna beam widths that are very, very wide, right? Typically 65-degree beam width. That means we're spraying uh, energy all over the place. How much of that is actually intercepted by the antennas that are in our user devices? It's a tiny percentage is intercepted by, even if you have 1,000 users in a sector or cell, the amount of energy that they are intercepting with their antennas is tiny versus the complete amount of energy or power that's being transmitted. So most of it's going out there and causing interference, all right? With beam forming using much smaller beams, right? Much smaller beam widths, we drastically reduce the self-interference. And so that causes an increased cell capacity and coverage that's system-wide. It's a huge benefit, okay? So beam forming taking off today has been taking off since 2019. And then massive MIMO, we keep hearing about massive MIMO. What is that massive MIMO? Well, what happens in LTE is that there's a rule, a hard and fast rule. Within a sector, you can never have two users reusing the same radio resources at the same time and at the same frequencies. In other words, they cannot use the same resource blocks at the same time. That causes interference. That's always been a limiter on the system capacity. What if you have 100 resource blocks? What if you had 50 resource blocks for 20 megahertz wide carrier or 10 megahertz wide carrier? Well, massive MIMO unlocks that, breaks that rule. What you can do is you use beam forming, because you can now put out these pencil thin beams. You can actually create isolation between multiple users using different beams. You can reuse the same radio resources at the same time. Imagine that. That can give you a massive increase in capacity. So massive MIMO is a combination of multi-user MIMO, giving the same radio resources at the same time to different users in the same sector or cell, and beam forming to make sure that we have orthogonality or separation between the users so we don't get interference. Okay, so this is what's coming out as well. So these are big advances in antenna technologies that we can now use in the cellular network. Next chart. So, okay, great. So we've got our spectrum. We know what kind of antenna techniques we want to use. What kind of impacts does this cause in the radio head? So we're already seeing beamforming plus 4x4 single user MIMO happening at millimeter wave. There are enormous RF channel bandwidths there. So in the millimeter wave, it's theoretically possible to deploy up to a 400 megahertz wide RF carrier, which is, again, I call it crazy talk. It's enormous, right? So haven't seen that happen yet, but have been seeing multiple 100 megahertz wide carriers being deployed. Multiple 100 megahertz wide carriers being deployed from a single AIR device. Okay, this is huge. In LTE, the limitation by standards is a 20 megahertz wide carrier. 20 megahertz wide carrier, and so backing up a second, what are the main considerations that will limit capacity and throughput? The first thing is carrier bandwidth. It's always carrier bandwidth, the number one thing we look at. The more carrier bandwidth you have, the higher the throughputs and the higher the capacity of the network, of the RAN. Okay. The second thing is modulation schemes. Can you use a higher order modulation scheme such as 256 quadrature amplitude modulation versus a QPSK? That has a huge effect. And what it requires, we can use those higher order modulation schemes when air interface conditions are good, when channel SINR is good. Okay. And then the third thing is the MIMO scheme. Okay. So we see up here going to much wider channel bandwidths. We see that we want to do beamforming, so we require many more antenna elements and many more transmit and receive paths or fine control. But also, we're going to have high signal loss inside radio circuitry due to the millimeter wave frequencies. Okay. So that's a big consideration. All these things here have to be considered when we're designing our AIR device that works at millimeter wave spectrum. And then massive MIMO happening at the C-band. Again, enormous RF channel bandwidths available. Expect 100 megahertz wide RF carriers. The ability to do that. So that you see the operators today in the US going after, they've already gone after C-band spectrum with recent auctions. In Europe, they'll be doing this in Japan, Korea, Asia, wherever you go, okay? And what we can support up here with massive MIMO, wider channel bandwidths, but also higher order MIMO schemes. And so we're seeing things like 32T, 32R in terms of the number of antenna ports, and 8 MIMO layers in the downlink. What you typically will see is for 8 MIMO layers in the downlink, you'll see 4 MIMO layers in the uplink. And then down here for 64T, 64R, 16 MIMO layers in the downlink, 8 MIMO layers in the uplink. So the tougher situation obviously is in the downlink. We've got twice the number of MIMO layers, so that's what we look at. And one of the things that's really important to understand at the physical layer, and most of the physical layer resides in the DU. Traditionally, it's all has resided in the BBU. It has resided in the DU. Now there is something called an option 7.2 split that's coming out, where a portion of the physical layer can now be in the radio head. Okay, so it's called upper versus lower physical layer processing. And with what's called a 7.2 split, some of the physical layer stuff goes into the radio head, but most of it's still in the DU. And what you'll see is that we see the physical layer processing scales with the MIMO layers and antenna ports. So this is important, right? So if I get 16 MIMO layers versus say 2 MIMO layers and 2 by 2 MIMO, that's 8 times the amount of information that has to be processed at the physical layer. Okay, so important considerations here. Next chart. So challenges for us in the distributed unit. So we have a wide variety of environments at the far edge. I talked about those 4 scenarios earlier, where I said 3 of them were benign environments, you know, the air conditioned and heated because people are inside it, the cell site shelter or the in-building room or the CRAN hub site, pretty benign environment. But these outdoor cabinets may require an industrial temperature range that goes down from minus 40 C to plus 65 C. So very cold to very hot. Of course, the requirement depends upon the geography of the network. If you're talking about deploying networks in the far north, all of northern Canada, call it in the Scandinavian countries, call it Northern Europe, call it Northern Asia, then they care more about the colder temperatures. Can the DU operate optimally? Also, can we do things like cold restarts and things like that? Can we do that when it gets very, very cold? They don't care that much about the hot temperature range. But now let's talk about, you know, the networks that have to operate in very, very hot climates. Let's imagine that it's in Southern Africa, right? Or South America, or places like that where it can get very, very hot, or Asia, doesn't matter, right? All over the globe, we're going to have portions of the geography where things get really hot. So we need the DU to keep operating at up to plus 65 degrees centigrade there, or Celsius, excuse me. Also, we may need to have very small form factor cabinets. So, you know, very typically 19-inch rack, one RU, one rack unit is a very typical way that we dimension things in terms of our servers. But what we're seeing is a requirement for reduced depth, going from things like 600 millimeters down to 500 meters, 400, 350, even 300 millimeter depth for standard 19-inch rack width servers, because bottom line is the racks get put against the wall, either in an outdoor cabinet or in a cell site shelter, and the ability for us to provide a reduced depth is very important. Also, processing power requirements are getting extremely large. I mentioned the physical air processing that has to happen in the DU. Also in the radio head for the upper PHY, right? So this is going to get large for millimeter wave C-band. Okay, so we have to take that into account. We work with our partner Intel. We are on a program called a platform called the FlexRAM platform that is provided and built by Intel. We are on that platform, so we work with Intel, Dell, and Intel have been partners for a very long time, obviously, in the compute industry. And so we work with them on what we need in terms of processing power. And then another thing to mention here is that power consumption is a big focus for operators. It has been for a while. It will continue to be. Sustainability is a big deal. And so we continually work on our plans for how to reduce power. So what you see here is I've got that, what's happening with these four considerations, the need for processing power, driving very high because of the new advanced antenna techniques. Chassis size needs to get smaller. The temperature range is expanded now, and power consumption needs to get smaller. So we need to keep working on that. Next chart. So challenges in the radio head and the UE. So we just said that with beamforming, and remember, we've got beamforming in millimeter wave. We've also got beamforming in C-band. We need many more antenna elements. And we can do this now because, especially at millimeter wave, the antenna element size is really tiny. And also in the 3.5 to 4.7 gigahertz range, much reduced versus what it was previously for your typical spectrum for LTE. And so we need many more antenna elements in there, many more antenna ports, and for things like antenna integrated radio head, that'll be inside the chassis. All right, many more transmit receive paths, more total transmit power across all the antenna elements. And so all these devices, antennas are really built with circuit board technology. If you look at going back a long time, if you open up a traditional cellular antenna, say at 700 megahertz or PCS band or AWS band or where the case may be, if you open it up, you'll see a giant circuit board. Okay. Well, guess what? Now we've got many more of these elements, many more of these circuits, and we have to maintain orthogonality across these circuits. We cannot allow crosstalk or interference between the antenna elements and the circuit tracers carrying those signals. We've got now is a situation where we have a much greater densification of RF circuits bundled into a small package. Must have zero to no correlation between them. Another way of saying no correlation, no interference or crosstalk between them. Okay, so that is a challenge. Next slide. And actually, I guess I'm about to turn this over to you, Madden.
Well, thank you, Charlie. That was quite interesting. I have a couple of questions for you before we go on to the rest of it.
Sure.
And I know there are questions on the channel as well, right? So
Okay.
to the audience, while I'm having a conversation here with Charlie, if you have any questions, please use the Q&A function to submit the questions, and we'll get to them in a few moments. We talked about, or you talked about increased speeds and stuff like that without quantifying them. What I've been seeing from the radio unit manufacturers are claims of over-the-air speeds of 4 gigabits per second to 6 or over 6 gigabits per second. And that's what they will say you get a user will experience. Now, what does that do to the transmission or the data speed that you have to handle in a distributed unit?
That's a really good question, Madden, and that makes sense. What we saw back in 2019 timeframe was the ability to achieve 1 gigabit per second. So now here, a couple of years later, I'm not surprised that it's up to the 4 to 6 gigabits per second in the lab for sure. What that does for us on the DU side is it drives much higher front haul throughputs. So that physical layer processing that I talked about, where you go to higher order MIMO schemes like eight layers or 16 layers, has a huge impact actually on the front haul interface. So I show here in this picture eCPRI, right? So we know that for LTE, we were using the CPRI interface. We know go forward into 5G, we're using the eCPRI interface. And it turns out that the couple of main considerations. The first one is the RF carrier bandwidth, right? We talked about in LTE is 20 megahertz or less. You can easily see 20 megahertz, 10 megahertz, 5 megahertz wide carriers in LTE. Now we're driving to 100 megahertz. We're not driving, we've already achieved that in millimeter wave, and we'll achieve that in C-band. So that has a huge impact on us in the front haul. And what I can tell you right now, for something that's, I call it the easy case, a 10 megahertz wide carrier, 2x2 MIMO, that we can cover that with a 400 megabit per second connection over eCPRI, 400 megabit per second. Now that when you drive, if you drive toward a 20 megahertz wide carrier, 4x4 MIMO, it multiplies that by 4. So that drives into a 1.6 gigabit per second requirement. And so, and those are relatively benign. So where we really get challenged is at the frankly speaking, is the massive MIMO. So if we look at something like a 100 megahertz wide carrier, 8x8, or excuse me, 8 MIMO on the downlink, 8 layers of MIMO, that drives us into a 25 gigabit per second connection. If you go to and that's 32T, 32R, 8 layers of MIMO, that drives us towards a 25 gigabit per second connection. And if you go to 64T, 64R, and call it 16 layers, over 50 gigabits per second. So it's, again, I call it the crazy talk thing, right? Imagine that we've got to provide a mid-haul transport connection for one radio head that's got to support up to 50 or even in excess of 50 gigabits per second. So it has a huge impact. Good question, man.
So at 100 megahertz channel, and you said you can get up to 400 megahertz, so that would be carrier aggregation across 4 100 megahertz channels. We're really talking about at the board level in excess of 100 gigabits per second. Yeah?
That's correct. And what we're doing is that we're sizing, believe it or not, we're looking at designs that can support 100 gigabits per second to 200 gigabits per second for the future.
Okay, so that's where we're going. Yeah, the second thing is you talked here about antenna integrated radios. So the antennas are typically microstrip structures where you have a circuit on one side and backplane on the other. And typically what I've seen of antennas is they tend to be very thin structures. But now you're adding a high degree of processing to this, right? It would seem to me that as you get to higher order multiple input, multiple output MIMO, you would want to have more of the processing right at the antenna so that you shorten your circuits, you reduce your time of flight or your delay, and you don't have to deal with these long transmissions between the radio unit and the distributed unit. So this would tend to be when we are looking at processors like server designs. These are multi-layer structures rather than single-layer structures. So we're now talking about in the packaging of an antenna integrated device or radio. Something has an antenna structure with a microstrip and then a multi-layer structure to really carry all of the processing. Am I getting that right?
I believe that's correct. I mean, I'll be really direct. I spend most of my time looking at DUs and CUs because that's what we make, right? We make servers for DUs and CUs. We're not a radio head company, but I agree with what you're talking about. And it's really just based on my past experience before Dell, right? Working in the industry that, I with this, there's many more circuits that we've got to have. I can see we got to go to a multi-layer approach as you're suggesting.
Yeah, I mean, that's pretty typical. Okay, so we'll get to questions in a couple of minutes. I'd like to just cover off a couple of things here from an HDP standpoint. Charlie has talked about what he's seeing the demands are in the industry. There are a couple of projects that we are looking at in HDP that are dealing with high performance stuff. One of them is the copper surface treatment versus loss, and testing this at 28 gigahertz and above. You know, the millimeter wave spectrum that Charlie talked about is really in the 26 gigahertz to 40 gigahertz range in the United States. Not sure where it is elsewhere in the world, but this is one of the things that we are focused on from the HDB standpoint that really will be applicable to antennas and radio designs. The second thing we're looking at from a performance standpoint is ultra low dielectric constant products and looking at the delays and how those materials behave. And basically measuring time of flight on circuits using low dielectric constant materials. On the high reliability projects, we're just talking about the need to integrate a lot of processing with the antennas, and the reliability of hybrid circuits using thermoplastic and thermoset materials is one of the key things that we have to understand. Now, in one of the key cost drivers for operators is failures in the field. If you have an antenna at the top of a tower with electronics, every time that thing fails, you've got to send not just a technician in a truck, but actually either a bucket truck if it's on a power pole, or a tower crew to go change this thing at the top of a tower. So that's a key consideration for operators, is reliability of the materials and the products that they're putting out in the countryside. And then the last bit of it, we talked about environmentally friendly products. We are examining a host of lead-free solders and the reliability of those materials in harsh environments, with a number of thermal profiles that we are testing over the next year or so. So these are just examples of projects that HEP is running right now that are directly related to what's happening in the industry with the emergence of 5G and where we go from here. So with that, I will turn it over to Larry for questions. Larry, you have questions, I believe?
Yes, there's been a couple of questions on the site. First one's from Joe Zhu. What is the mid-band range, 900 megahertz to 6 gigahertz, I guess?
Yeah, that's a good question. So the mid-band range really starts around 2 gigahertz. So the old and these things keep changing, right? So a couple of years ago, mid-band was just, actually for some operators, 2 gigahertz was high band, right? Because we typically had the low band, which is 600, 700, 800, 900 megahertz. And then we had things like AWS, PCS, or 2100 in Europe, or 2600. Those would have been called high band. But now that we've gone up into this, frequency range 1, frequency range 2, the mid band has expanded, and so the expansion takes us now from the mid band is now about 2 gigahertz to 6 gigahertz roughly. More directly, like AWS, for example, extends down to 1700, right? So the devils are in the details. Basically it's 2 gigahertz to 6 gigahertz is the new mid band, and the millimeter wave is the new high band.
Okay, thank you. Next question is on slide 14. Would you be able to share some details on the type of integrated antennas used, patch or dipole? I think we addressed a little bit of that.
Yeah, I mean, since we don't make radio heads here at Dell, we don't manufacture them, I'm a little bit of more of extrapolation from me. What I've seen in the past is a combination. It depends. When you say patch, to me that means a two-dimensional antenna, right? So basically built with the trace. What I've seen is that if it's a very highly optimized antenna for a very, very specific range, patch for sure. But if it's for something where it has to operate over multiple carrier bands, it turns into a mixture of patch and a raised dipole, if that makes sense. So one of the things the operators are always trying to do, they're trying to reduce their footprint on the tower. And we know that they pay their leasing costs based on how much equipment and how much load is on the tower. And what's gotten crazy is that you've got a lot of big operators now with 6 or 7 carriers deployed. And if it's a 3-celled or 3-sectored site, so 3 cells at call it 6 carriers, those are radio heads that are single band, single carrier. There's 18 radio heads in the tower. They have to pay for every bit of that space and weight and load that goes in the tower. So they really started working hard on multi-band approaches, multi-carrier. And so that has happened already. We're seeing multiple carriers being handled by the same antenna panel and the same radio head. And what I see when they start combining those things, they need to have more of a 3-dimensional dipole. It's kind of a hybrid patch and dipole. Does that make sense? So it really depends on the exact implementation.
Okay.
Makes sense to me.
The last question I have here, is there a conflict in the lower DK and the larger antenna pads? How do you compromise?
The lower DK, what does that mean?
Lower dielectric constant. Yeah.
Oh,
Uh,
I don't know if that's a combination of both of us answering this one, Madden. I'm not sure. But the lower the dielectric constant, that means the slower the speed of propagation, right? Back, or is it the other way around?
That's a good question. I think what we're trying to get to is if you can use lower decay materials, you would get higher density structures. But yeah, it's how you get to a match. It's how you get a matched impedance at the end of the day, because you have to be able to run at the right impedance and not get any internal reflections.
Right. So for me, that was a little bit hard for me to answer.
Yeah.
I think, man,
So,
you a better answer than I did.
Okay, that's all. One more, lower DK means faster signal speed and propagation. Yeah.
Okay.
That's all the questions I have. Heading back to you.
okay. Well, thanks, Larry. Well, so where are we? We're at the end. So first of all, I'd like to thank Charlie for taking time today to share his insights with us. Thanks, Charlie. That's very interesting. I learned something new every day, and I certainly learned something new today. Over 100 gigabit per second on the circuit boards is going to be interesting. Yeah.
Yeah, absolutely.
I'd also
You're
like to
welcome.
thank. I'd also like to thank everyone for attending today. So I hope this was useful, and we will continue doing these as we have opportunity to. So thank everybody, and that's it for us.
Yeah, one other item, we will have the presentation posted on the website along with the recording of the session today. So if you check tomorrow, it should be posted up on the website. Thank you.
Thanks, Eric.
Thank you.